Suppose you work for a company and you produce some commodity, and the monthly production costs vary depending on how many units you produce. The more units you produce, the more it costs. And there are also some fixed costs involved, and also some variability in the cost per unit due to cost of raw materials varying and any number of other factors. So you'd like to model the cost as a function of the units produced. This will allow you to make predictions or forecast the production costs given the number of units produced. You have some data from past months. Well, we can use this to develop a mathematical model. Fortunately, Excel does all the work for us. We'll be working with the Excel file cost estimate, which you'll find in the class 10 plus folder. A first step in modeling is often visualization, so that's what we're going to do first. So in this worksheet, we have the monthly cost based on the units produced, and these are actual units produced and cost data for previous months. The first thing we're going to do is plot the data with a scatter plot. So I select the data including the column headers, and I'm going to go to the Insert tab here. We're going to select Scatter Plot. So what this does is plot the data with the units produced on the x-axis and the monthly cost on the y-axis. Each data point represents units produced and a cost. And if you mouse over, you can see the values. Now we can see that the data vaguely seem to be increasing, which makes sense as the cost increase as the units produced goes up. So we're going to fit a line to this data. So we're going to fit a linear model, and to do that we'll mouse over any of the data values and right click, and we're going to select Add Trend Line. And you see that we have a number of different models that we can select from. We're going to focus on the linear, and a little bit later we'll do the exponential. So the linear model is the simplest. And I'm going to select display the equation on the chart and also display the r² value, and I can close this off. I'll move this, and we can see here we have the equation of the line. So this is our model. We'll talk about the r² value in a little bit. X is the number of units produced, and Y is the cost. Excel displays the equation of our model right on our trend line chart. We can also find the slope and the intercept using Excel functions, and we'll have reason to use that. So the equation for slope is just slope. And we need to enter the Y values first. And I'll include this missing value here. Excel will ignore that just because I want to include the entire data range. The Y values first and the X values second, and there's our slope. For the intercept, well, that's just intercept. Okay. Again, known Y's and known X's. So using these values for the slope and intercept, we can find the predicted costs for every value of units produced. And so the way that I'll do that is that, let's see, y equals mx. So here's my x values, the units produced, and I'm going to multiply by the slope, and then I'm going to add the intercept. Okay, so since I'm going to copy this formula down, I would like to lock. I need to lock the row. I need to lock that, and I need to lock this guy. So you can see our predicted cost, and this is the actual cost versus the cost predicted by our model. All right. So now we'd like to get an idea of how good our model is. From the look of the data and how scattered they are, it doesn't look like our model is all that great. So introducing some notation, we'll let the x1, 2, and 3 denote units produced at month 1, 2, and 3. And the y's will denote the actual costs. And we'll use y hat to denote the predicted values. So we see in month 4, X4 is 873, and Y4 is 8,000, and Y hat is 9401. So that's the value predicted by our model. The error, or the residual, is simply the difference between the actual value and the predicted value. So here we see Y4 minus Y4 hat is minus 1401. To get an idea of how good the fit is, what we want to do is look at all of these residuals, which are the difference between the actual value and the predicted value, and then we want to sum the squares. This should remind you of the standard deviation formula. And the reason we sum the squares is because if we simply summed the residuals, then the ones that are negative would tend to cancel out the ones that are positive. In fact, we would just get 0. So this is what the sum of the squares of residuals look like. We can get a measure of our goodness of fit as the standard error, which should remind you of the standard deviation. Here's a formula, but we're going to do this in Excel, so you don't need to memorize this formula or anything like that. And we're going to get an empirical rule type result, which tells us the percentage of data that will lie within 1, 2, or 3 standard errors of the predicted value. So we can find the standard error in Excel. So I'm going to come over here, and it works the same way. Let's see, it's STEYX. So that's, in other words, standard error YX. And again, you want the known Y's and then the known X's. So that's our standard error. We can also find the residuals, or just the error values for each of our values versus the predicted value, just by subtracting the actual cost minus the predicted cost. All right. And here we see that our residual for the example we looked at, Y hat 4, or Y4 hat, is minus $14,001. Here's an example. We're 95% certain that the cost when producing 600 units would be between what two values? Well, we know what the predicted value would be just by plugging into our model, and we know what the standard error is. Let's come over to Excel. For 600 units, the estimated or predicted cost is going to be 600 times our slope plus y-intercept. So this is our predicted cost, and we want values within 2 standard deviations of that. So I need to add and subtract 2 standard errors. Okay. Here's our standard error right there. So the lower limit, or lower value, is this here, and the upper value will be given by that predicted value plus 2 times our standard errors. Okay. So we can be 95% certain, approximately, that if we produce 600 units, the cost will be between these 2 values. So we've just found Y hat, and then we found the standard error. We found 2 times the standard error, and then we added and subtracted that value from Y hat to get our range of values within 2 standard errors of our predicted value for 600 units. Should remind you of a 95% confidence. Another measure of goodness of fit is called the R-squared value, also called the coefficient of determination, but almost nobody uses that term in practice. Intuitively, it's the percentage of variation of the data that is explained by the model. So if r squared, being a percentage, it's going to be between 0 and 1. If it's close to 1, that means the model explains a lot of the variation, which is a good thing. It means our model is good. If r squared is not close to 1, then there's a lot of variation that is not explained by the model, so the model is not such a good fit. For our model, we found the r squared value to be 68.82, so about 69% of the variation explained by our model. So about 31% not explained. So that's not that good. It's not terrible. Unfortunately, there's no rule of thumb for what constitutes a good fit. It's just if it's close to 1, it's good. So we'll call our model seems to be about mediocre. You could think of it as exam scores. If you got 90%, that's pretty good. As usual, there's a Excel function for computing the r squared value, and it's just r squared, RSQ. And again, you have the known y's and the known x's. Okay, and there's our 68%. So it's easy to interpret because we're familiar with percentages. The standard error, on the other hand, is a little harder to get a handle on because it depends on the actual data values. On the other hand, the standard error allows us to find those confidence interval type ranges of values. We can also determine whether our data values are outliers or not by using our 2 standard error rule. Anything that's outside 2 standard errors would be considered an outlier. So we'd like to see if this error that we found is greater than 2 times the standard error. So we can do that with an if statement. So we could say, and we want to look at the absolute value. We can use our ABS function. So we want the absolute value of the error. And so our logical test, if that is bigger than 2 times the standard error, the value, if true, is what? We're going to call it an outlier. And the value, if false, is not outlier. All right. So it looks like everything is an outlier. Well, you could probably imagine what I did wrong here. I forgot to lock my rows. Okay, so we need to go and lock the rows. All right. Now let's see what we get. So most of them are not outliers, but the last 2 are. Well, the last one here, it's no mystery why that's an outlier. We didn't even have a monthly cost, so this is not going to be reflective of anything. So it seems like all our actual data values are not outliers except, or none of them turn out to be outliers, okay, which is not surprising. We actually got 100% of our data values within 2 sigma. So we looked at linear models in Excel. We generated trend lines. We looked at a couple of measures of goodness of fit, which we used to determine the accuracy of our predictions. We had an empirical rule type result, and we looked at some Excel formulas for computing these values.